And what we observed is a quite good match for the model predictions shown in red and the results from Planet Lab. What we did not have was an exact match of the model predictions or the Planet Lab results to the results of our national testbed. We're currently just about to find out what this means, and we're currently about to adapt the model to add some more degrees of freedom to match both cases. But I think it's just an interesting point that if you rerun experiments on two different testbeds and you get different results, then we will clearly have to be very meticulous when we want to run testbed experiments to verify mathematical models. So, second part of my talk will be on security in mobile ad hoc networks. So just for the basics, since mobile ad hoc networks are completely infrastructureless, the nodes have to act both as communication endpoints and as routers. So if two nodes want to communicate and are not in direct transmission range, then the nodes in between are required to relay the transmission. This means the routing in a mobile ad hoc network has to deal with a constantly changing topology, so it has to deal with a very high dynamic, and there are on an abstract level, there are two approaches to deal with this. One is the proactive routing, which broadcasts link state information periodically, and so a route will be available before it is needed. And the other one is the reactive approach, in which a route is looked up at the point it is requested. And this is in fact what I will use in the following. So I will use ADV, and it works just like if I have a source that wants to communicate with a destination and no route is available, then a route request will be sent as broadcast, and as soon as the route request reaches the destination, a route reply will be generated, and this route reply will be sent back, and with this a route is established. So to minimize the broadcast overhead for broadcasting the route request, ADV will use an expanding ring search. This means we will start looking for the destination in an area close to the source, and if it is not found, we will increase this area in certain steps. So we will use this later on. So regarding security of mobile ad hoc networks, in fact, due to the wireless multi-hop communication, and if you consider devices from many administrative domains, then mobile ad hoc networks are vulnerable inherently. So in fact, each layer is affected by new types of attacks. We have simple jamming on physical layer and medium access layer. We have more sophisticated means, for example, a transport layer. If you just delay TCP acknowledgements, then you will start the TCP fallback mechanism, and you will decrease throughput in the network. And these are attacks that become available due to the wireless multi-hop nature. So what we consider is attacks on routing layer. These are in general based on injecting false routing information, and one attack that I will use in the following is the black hole attack. Just like a black hole in terms of astronomy, black hole in a mobile ad hoc network tries to attract traffic and does not forward it, but just drops it. And in this case, it's quite straightforward because the black hole is closer to the destination, so the route appears to be better, shorter, more reliable, and the source will choose this route. Anyway, the black hole can lie about these routing metrics and pretend to have good routes to any possible destination, and with this attract traffic, and then if it comes to the data exchange, it will not forward the data, but just drop it. So question is, how can we deal with misbehavior in mobile ad hoc networks? How can we exclude misbehaving nodes, since mobile ad hoc networks are vulnerable inherently? In fact, there are two approaches. One is intrusion prevention. Other one is intrusion response, intrusion detection combined with intrusion response. So intrusion prevention is usually based on secure routing protocols, and these use means of cryptography to secure route discovering and to secure routing tables to prevent false routing information from being injected or correct routing information from being altered. Question is, if we use this on routing layer, on network layer, how can we prevent attacks on other layers? And in general, this is not possible by secure routing protocols. Another example are secure ADV and Ariadne as a secure version of DSR. And these protocols have been designed very, very cautiously. In fact, still attack vectors have been identified recently that are able to circumvent the cryptographic mechanisms deployed in these protocols. So what I will talk about is the second alternative, intrusion response. There are several approaches available. The first one was, in fact, watchdog path rater, proposed by Marty. And this is just, if we consider the black hole attack, the intrusion response works just like overhearing whether a node relays the communication correctly or not. So if I send to my direct neighbor a packet for forwarding and assume symmetric wireless link, which is in fact good assumption, because if we consider 802.11 with an RTS-CTS sequence, we need a symmetric wireless link, then I will be able to overhear whether my neighbor relays the communication or not. So, and if it doesn't, I can just mark it and say, okay, bad one, don't use it for routing. Subsequent approaches like confident co-notion, they try to overcome some drawbacks of watchdog and path radar, but they are still based on this overhearing approach for intrusion detection. What they all do is to use an address-based approach for intrusion response. So to exclude a misbehaving node from the network, they just say, okay, this is a bad address, do not send anything to this address or do not receive anything from this address. The question is, if we are in a network where we need the cooperation as a basis for functionality, and if we have devices from many administrative domains, so in general, a user can just do whatever he or she wants with the device, then changing addresses is possible very easily, may it be on a medium access or network layer. And with this, we can just bring down the effect of address-based intrusion response mechanisms. So we said, okay, let's try it another way around. Let's try some location-based intrusion response. And the idea is quite simple. We set up quarantined areas. If we detect misbehavior in a network, we define a quarantined area where the misbehavior happens. And this is, in fact, a three-step process. We have to establish these quarantined areas and to interrupt routes that are affected, so that cross these quarantined areas. Second step, we have to establish routes that do not cross these quarantined areas. And for ADV, we do this just by restricting the broadcast of a route request message. So every node located within a quarantined area is not allowed to relay route request messages. And with this, the route established will just go around the quarantined areas. And in a third step, since we assume that tracking of the nodes is not possible while they're quarantined, so if there is no communication, then you won't be able to determine locations. We have to revoke these quarantined areas after a certain amount of time, because otherwise what will happen is, since we are in a mobile environment, the misbehaving node will move, will have a new affected area, will become active again, will become detected again, a new quarantined area will be set up, and with this you start to partition your network, and this is what we want to avoid. So we revoke these quarantined areas after a certain amount of time. So also for mobile ad hoc networks, I want to talk about evaluation issues. Mobile ad hoc networks are not this widespread in real world right now. There are some, but they are designed for real data transmission, and the people running them wouldn't be that happy if we want to implement attacks and countermeasures within these networks. There are a few testbeds available, but these are usually designed specifically for the needs, so for the research that should be done within these testbeds. So the results would be comparable, very hardly even worse than for the peer-to-peer case. So we decided to go for simulation studies and for analytical models, just to have two points of view on the problem. So both simulation studies and analytical models have to make abstractions, simulation studies, because otherwise you will have runtimes that are not feasible anymore, and analytical models just because you won't be able to handle everything from data transmission up to routing protocols. So since simulation studies can only cover some small portion of the parameter space, we said, okay, we will have an analytical model to cover the rest. So these are simulation results from the studies we did for the location-based intrusion response. We had a scenario consisting of 1,000 nodes, 7 to 8 neighbors per node. This means we just have a connected network, so the probability for having a route between arbitrary nodes is some 99.9%. We have a mobility with pedestrian speed, and we have 1 hour simulated time per parameter set. So what is shown here is the results for a defenseless network when you increase the number of black holes considering the loss that is caused by the black holes. And you can see that just one black hole in our scenario consisting of 1,000 nodes is able to attract more than 60